Okay. Thank you very much for the invitation, and thank you very much for waiting 2 weeks after all circumstances. And I would like to present this work, a unified approach for solving sequential selection problems. This is joint work with Alexander Gondeshluger, University of Haifa, and Asaf Zevi, Columbia University. And we started to work on this problem when I did my sabbatical semester in the fall 2018 in the Haifa University. So I will briefly describe outline, and outline its sequential selection problems. And what we're doing, we're proposing solving sequential a large class of sequential selection problems by unified method. And this unified method based on sequential stochastic assignment problem with fixed number of jobs. We will reduce all problems of a particular class to this method. But when we would like to discuss also sequential stochastic assignment problems, we would like to solve sequential problems with fixed horizon, but we also would like to solve sequential problems with random horizon. And in this case, we need extension of sequential stochastic assignment problems to the case of with fixed horizon to random horizon. And generally, this problem was solved by different method in literature, but in generally, our contribution here also that we're going to show that sequential stochastic assignment problem with random horizon, its particular case generally with fixed horizon is appropriate translation. And then I will demonstrate this method on some example. An example of the particular pick, it's selection of k-based values with random number of alternatives. It's random horizon. And also I will discuss in most of the work discussion of sequential selection going to be by two parts. First part, major part, is going to be sequential selection, which is going to be based on the information as a relative ranks available to observer. And the last part, all these problems, I will explain that all these problems also can be solved with the full information when someone can see all filtration included variables, random variables itself. So this more or less outline. And as example of sequential selection, it's we observe sequentially the observations, and our goal is and it's irrevocable in the sense that we need to decide to stop or continue to observe. And when we stop, we observe reward on at the stopping time. Now, as example, is search apartment San Francisco, so it's very tough market, for example, and more or less you need immediately to decide take or not to take. If you don't take, it's more or less gone. Another class of problems, it's sequential testing related to quality control or debugging some products, or for example, the selling of asset when you try to it's a famous problem in the stopping problem in the selling of asset, and here can be one stopping time or can be multiple stopping time when you, for example, have few assets and you would like to sell them, and then each time, if it's irrevocable, you need to decide sell or not to sell until you sell all your assets. And horizon here also can be fixed. You can do it for fixed number of time or for a random number of time. So this more or less kind of motivations of these problems. Now, generally, classical sequential selection problems in literature, it's from 50s, it's secretary problem. And this problem I will present and discuss, and it has different approaches of solving different sequential problems, mostly case-by-case method. So each problem depends on information, and depending on reward function, solved in literature case-by-case. So what we try to do generally, we try to solve all different problems by one method. And it's kind of, and we're also, our proposed rule always of the same type. It's kind of memoryless threshold rule. And other problems, it's no matter what is the kind of problem, and I will present in a few minutes. Generally, when solving by case methods, some rules was pretty complicated, but our rule always has the same form. Now, in order to start, I need to some introduction, and then having this introduction, we can proceed. Now, as I said in the beginning, I will present everything related based on the available information as a ranks, relative ranks. But then I will switch at the end of the presentation and show that more or less the same problems can be solved also using full information. But from beginning, everything going to be presenting as a relative ranks. Now, suppose x1, x2, so on, infinite sequence of independent identical distributed random variables defined on some probability space. Now, a relative rank RT, it's sum of indicator functions that xt less or equals xj. So it means if up to time t, xt's largest observation, a relative rank going to be 1. If it's second largest observation, a relative rank going to be 2, so on. Now, absolute rank of observation t among all n observations, exactly defined by the same way, only sum is running between 1 to n. So it's absolute rank, which we don't observe generally. And it's clearly that absolute rank, by this definition, at least has the size as a relative rank. If time t relative rank equals to 1, so absolute rank of xt going to be 1 or more. So it's now this quantity has some kind of properties, and the main property is based on Rény's theorem. And Rény's theorem states that relative ranks were independent, uniform distributed on the integers 1 to t. Now, it's not complicated result to prove, but it's basic result that's useful in the calculations. And second result, which straightforward calculation, more or less using base formula, a probability that absolute rank at time t among n equals to a, given all history of relative ranks, only depends on the relative rank. It's very intuitive, depends on relative rank at a value of relative rank at time t, and given by this combinatorial formula, which straightforward can be calculated using these assumptions that x1, x2, xn, and id are continuous random variables, with probability of Thias is 0. Now, in the beginning, we will assume that only variable information, as I said, it's relative ranks. Now, and some notations that to use in the results in the presentation, we denote by RT and XT the sigma fields. First one generated by relative ranks up to time t, and all observations itself up to time t. And also we denote by R and X the corresponding filtrations. Now, the class of stopping times of filtration y, we denote by tau y. So this is class of stopping times, which is it means I event at tau equals to t belong to yt for all t between 1 to n. Now, using this notation, possible to before we discussing the reward functions. Now, a sequential selection depends on the two main features. First, it depends what is our reward functions that we're interested in, and then second, what is the available information. So our problems which we only relative ranks are observed cause no information problems, and the problems when the axis itself observes course, full information problem. So now I'm going to present everything in the terms of no information and then switch in some case to the full information case. Some questions? Maybe. Okay. So so with two problems related to the average reward. Now, first problem going to related to fixed horizon problem, and fixed horizon we can formulate in this way. So suppose n is a fixed positive integer, it's our horizon, fixed horizon, and q its function from the integers 1 to n to real line. Now, every reward of the stopping rule tau, which is based on filtration based on relative ranks, is expectation of q of absolute rank. And we want to find the stopping rule tau star such that this expectation going to be maximal. And we would like to compute optimal value of the reward function. And I will show shortly a few examples of such functions q. For example, in the secretary problem, we would like to q, its indicator functions at absolute rank equals to 1. And we would like to maximize probability that absolute rank equals 1. So expectation of indicators exactly are this probability. Now, if you think about secretary problem, if horizon is fixed, everything is defined well in this page. But if horizon, yes.
Can you remind us what is the secretary problem?
Yes, so secretary problem is following. Suppose we have n candidates, and you can and this think about that its candidates as kind of values, particular values, which is independent equally distributed. Like we did exam and this outcomes of exam, but you don't see what you can see. You sequential observe only relative ranks. You see first candidate, and when you see second candidate, you can only compare to the first candidate. And now, what you generally interested, you want to pick up the best candidate, which has absolute rank 1. Now, but observable information, it's only relative ranks. Now, and this is your problem. You want to maximize probability to stop. In your decision is irrevocable. When candidate is coming, you immediately need to decide to take, accept, or reject. And you cannot go back, and also it's anticipate. You cannot see the future. And then the problems find the optimal strategy to select the candidate with absolute rank 1, such that maximize probability of selection, and calculate the value. Now, this problem is solved by different methods. And one, it's a dynamic kind of backward induction. And another method proposed by Dimkin in the book with Yushkevich, macro processes. And with different methods solve this problem. In generally, optimal strategy in the secretary problem, you need to reject certain number of candidates. And this number that reject, it's function of the total number that you of your horizon. And then stop first time when you see relative rank equals to 1. And asymptotically in the secretary problem, you reject about n over e number of candidates, and probability of selection of absolute rank 1 under this optimal strategy is 1 over e.
Thank you.
Please. Now, the problem in kind of like in secretary problem, everything is good, but everything is working well if a number of candidates is fixed. You know in advance that you're going to have 100 candidates. But now, if number of candidates now is random variable, it's not fixed in advance. A problem should formulation of the average reward should be changed, and here attempt to explanation how to introduce notations when horizon is random. So in case of random horizon, everything depends on event. Let's assume that n is a total is random variable, a number of candidates, and n it's positive. It's random variable now, and has values 1 to n max. In general, theoretically, n max can be infinity, Now, and we assume that n and relative ranks, they independent. And now we need to introduce notation for absolute and a relative rank in the case this horizon is random. And everything is related to event n equals to k. So if number candidates equals to k on this event, we put absolute rank equals to 0 if time more than k, because it's impossible. After time k, you're not going to see everything, because on event n equals k, maximum number of candidates can be 1 to k. And also relative ranks notation also need to be changed. On this event n equals to k, new relative rank bar equals relative rank is based on previous definition when time up to maximum number of candidates, and it equals to 0 otherwise. So, and then we also need to introduce new sigma algebra based on R1, RT bars. And also we need to introduce, and this is what we need to introduce, new sigma algebra based on the R1 to RT bars, when T running between 1 to maximum support of the horizon. Now with this new notation, now we can also discuss average reward at this case. An average reward in random horizon is following. Suppose n is positive integer random variables with known distribution gamma, and the gamma k is probabilities at n equals to k. When k is running 1 to n max, its maximum value of support. And we assume that n in excess way independent. N in excess way independent. And now our reward function, it's function from the integer 1 to n max union with 0 to infinity. It can be only a non-negative outcome. And let's define a qt. It's a q of absolute rank on the event n equals to k. And also, in this new notation, we also would like to maximize its expected reward and find and compute optimal value of a reward on the new notation. Now I will show examples, and maybe it's going to be more clear all these signs in the examples, and then how we proceed. Now, as examples, a first example, it's selecting one of the k-best values. So in this case, a reward function of its indicator functions at absolute rank less or equals to k. And we would like to maximize the probability to choose a candidate with one stopping, such that absolute rank of this candidate at most k. And choosing stopping time is with respect to the stopping time, which based on the filtration based on the ranks. As I said before, case k equals to 1, so absolute rank equals to 1, less or equals, it's equals because it's starting with 1. It's exactly secretary problem. And this is exactly case k equals 1, a classical secretary problem that I defined. And the limit probability, it's 1 over e. Now, in the literature, there's not so many extensions to the, mostly a case with the random horizon is investigated only in few papers, case by case manner. And this case of secretary problem was investigated in literature by Pressman and Son in 1972. And they found, and they assumed different distributions for the number of candidates. And for example, in one, they have three examples. One of the examples was uniform distribution 1 to n, and then found, in this case, the strategy exactly the same. You pass certain number and then stop with relative rank equals to 1. And then a probability to get to stop before horizon finish, and also to obtain absolute rank 1 equals 2 over e squared. It's a little bit less than, this is about 37%, and this one about, I think, 27, I think it's 27, 29%. So, but the strategy is the same. Now, if distribution is not uniform, we also show that strategy not necessarily to be the same. It can be, you can, in the beginning, you can, you need to pass set a number, rank them, but didn't take them, and then you can stop in some island, and then again not stop, and then again stop. It can be islands between of the stopping times. So what we're going to suggest, our strategies, we're going to suggest, or we're going to be threshold. You're going to stop if you cross particular value, and I will show you as a more particular it in a little bit in few minutes during the talk. Now, only not to forget to say, our first problem, selecting one of K's best values, in literature discussed in two papers. One is Gilbert and Mosteller, it's not written here, in 1966, in JASA, Journal of American Statistical Association. It's one of the examples, but the full proof is in the same year, absolutely independently, of course, it was done by Sabir Guseinzadeh in theory probability in these applications of optimal strategy and the optimal value. He also investigated it for the case, for the k equals 2, he gave also asymptotic results, not only finite sample. So these examples of now in our example, it's example of minimizing of expected rank. So what we try to do, so largest observation, as you remember, has absolute rank equals to 1. Therefore, in our example, it's to minimize expected absolute rank. So in 1966, Herbert Robbins and co-authors published in the Israeli Journal of Mathematics result, which says what is optimal strategy and what is the value under this optimal asymptotic exact value and asymptotic value under this optimal strategy. And for example, asymptotic value, minimum absolute rank under optimal strategy going to be about 3.8695. This is the result, and it's asymptotic value exactly equals this expression, which can be evaluated up to 4 numbers. Now, Herbert Robbins, when published the paper in 1991, saying that, for example, if you try to minimize expected value of square of absolute rank, this problem is open. There is no optimal strategy is known. So in this case, it's a case we can suggest by proposed method solution also to this problem. In the previous problems with random horizon with different configuration. Now, in our problem, it's full information problem. Until now, everything presented in the terms of the information based on relative ranks. Now, full information problem, it's following. Suppose in this example, I decided to present the problem which published in the Annals of Probability by Bruce, which the paper calls sum the odds and stop. And problem can be presented in this way. Suppose you have Z1 to Zn, independent Bernoulli random variables, with success probabilities P1 to Pn. Now, again, you observe Z1 to Zn sequential, and you would like to stop with last success. So what you want, based on information, on full information, by observation Z1, Z2, and so on. And what you want to maximize, you want maximize probability, find the stopping time tau, based on full filtration, based on full information, such that probability that Z tau equals to 1 and rest of this until n equals to 0, it's maximum. And Bruce solved this problem and presented optimal value. So what we can do, we can also, by unified approach, we can solve also this kind of problem and present optimal value. And our recursive formula are going to give more or less closed form solution also in some sense. It's going to be closed form solution. Now, of course, it can be by unified approach can be extended to the case when n is not fixed in advance. Okay. Now in order to solve all these problems, I need to introduce sequential assignment problem, because what's going to happen, all our problems which related to the all sequential problems can be solved by this method. And this method, it's known method in literature, and we're going to extend it to the random horizon and then show reduction to this method. So it's kind of separate now a little bit topic, but then I will show reduction of all class of problems to this method. And this method called sequential stochastic assignment problems with fixed number of jobs. Now, fixed number of jobs going to be corresponding to fixed horizon, and then we going to extend this method to the random horizon. Now, and now I'm going to problem going to present it separately and then reduced. And in classical notation, which published by Derman, Lieberman, and Ross in 1972 in Management Science, a problem can be formulated in following way. Suppose you have n jobs, and each job t corresponding to random variable yt. So they assume that all y's IID random variables, and suppose you have some workers which has values p1 to pn, and these workers, this value is available. It's not probability, it's any values p1 to p. Now, when job t is arriving, so observation yt is arriving, you need to decide which worker going to be assigned to this job. If you decide that when job t is arriving, you assign worker j, so when you have outcome pj times yt, and worker j not anymore available in the future. So you already use this worker, it's not available in the future. Now the goal is maximize total expected reward. When, again, when job arriving, you assign worker not anymore available, and then you want to maximize total expected. And this calls sequential stochastic assignment. Now, so what are you looking for? You're looking for assignment policy pi. It's permutation on the values of the workers such that you can assign them and then maximize reward. Now, in 1972, about the same time, Albright extended this problem to the case when jobs still independent, but not necessarily identical distributed. So, and again, in the classical notation, you have y1 to yn integrable independent random variables, not necessarily identical distributed. Each y has distribution ft. Available information, again, it's sigma field generated by time t, sigma field generated by 1y to yt. Now pi is permutation on integers 1 to n, and you're looking for assignment policy workers to. So this is kind of general formulation of the problem. And then we're going to call this problem assignment for AP1 because it's fixed number of fixed horizon, fixed number of jobs. And because values of P is available, we can assume that we can assume that P1 to Pn located in increasing order. It's without loss of generality. And we're looking for the maximized expected reward. We're going to call it Sn pi, and looking for the policy pi star optimal policy assignment policy. Now, the problem solved originally by Derman, Lieberman, and Ross, and then extended for the independent but non-identical distributed random variables, as I said, by Albright. And solution is a very elegant solution. Of course, depends on the distribution of these random variables. And solution is following. It's solved by backward induction or dynamic programming. In the beginning, you need to find values A 0, A1 to AN, which form n intervals from any intervals. And when first y arrive, you look which interval it's going to fall. And because p values of p located in increasing order, you exactly assign value of p. For each interval, you have exactly one value of p, p1, p2 to pn. When first y arrive, you see it's arrived in interval number 5, p5 going to be assigned to this y. When it became non-available, and you recalculate all these values, and now you need n-1 intervals. And you're going until last one going to be assigned this last one without any choice. Now, how to find this A? A was found exactly using idea of backward induction, more or less for the proof used idea of conditional expectation and rearrangement inequality. Now, rearrangement inequality, it's inequality if you have two sequences of integers and you multiply one by one with each sequence and take a sum of products. To maximize the product, sum of products, you need to multiply larger by larger, second larger by second larger. This idea was used in the proof. And this is exactly a recursive relation to find these values A each time as a function of distribution. What is interesting, values of A each time, finding of values only depends on distribution. It doesn't depend on values of P. Doesn't depend on values of P. So this was the result of Delman, Lieberman, and Ross and Albright for the different distributions. Now, in last stage of process, in stage n+1, you exactly obtain expected value of optimal expected value. Remember, in the formulation of a problem, we assign to yt worker pi t. So in another formulation, worker j assigned to the index vj. So on the optimal strategy, last step of algorithm gave, because expectation of sum is always sum of expectation, optimal strategy gave generally gave exactly value, optimal expected value to assign to the worker j. I will demonstrate it to be more clear using the example. Think about this example. We have 3 uniform random variables, in this case, independent 0, 1. Now, first, we have 3 intervals. First interval going to be 0 to 3/8, 3/8 to 5/8, and then third interval 5/8 to 1. Now, when first y arrived, depends on interval. If it's 4 to second interval, you assign P2. If it's false in the first interval, P1, and third, P3. When it became unavailable, you have only 2 intervals. And these two intervals, it's 0, half, and half 1. And when second y arrived, if it's below half, you assign smallest p. If it's above half, it's largest. And last y when you arrive, you assign last p that you have in reserve. And then last step of backward induction gave this is optimal expected values and the optimal expected reward. Exactly, this is last step of interaction going to be P1 times this quantity, P2 times this quantity, P3 times this quantity. So this demonstration of Olberg, of Delman, Lieberman, Ross procedure. Now, when we did the same with now we needed to extend sequential stochastic assignment problem to random number of jobs. Now, in generally, annotation going to be very, very similar to the previous case when we have random number of jobs. And I'm going to shortly explain notation and then demonstrate using some example and show reduction, how we can reduce the problem. So again, let's n be positive integer value random variables with known distribution gamma. And now y1, y2 again is sequence of integrable independent random variables with distributions f1, f2. This we need different distributions. We also need to be consistent with the reward function to assume that probabilities is yt equals to 0 for all t. Now, the main assumption here that n horizon is independent of a sequence of y's. And again, on event n equals to k, when horizon equals to k, y bar t going to be equals yt if t below less or equals k, and 0 over y. So 0 in this case that you pass no one arriving anymore. We say we stop with the 0. And yt bar is a sigma field generated by one bar yt bar, our available information at the time t. And the sequential assignment problem in this case going to be exactly the same formulation, only horizon here, it's not fixed, it's random. It's random. And we would like to find the optimal policy based on available information, which is sigma algebra at each time t sigma algebra generated by y1 bar to yt bar. This is formulation of the sequential assignment problem with a random number of alternatives. Now, to completeness, I need to say a few things about the sequential assignment problem with random number of alternatives. Generally, original literature of the problem was solved by Sakaguchi in the Mathematica Japonica 1984, and he used a dynamic program. Now, in the 2010, Nikolaev and Jacobson suggested solution by reduction of the problem to the problem with dependent random variable, a kind of auxiliary assignment problem. So our kind of contribution here, in some sense, that we solved by method of Derman, Lieberman, and Ross. So what we show that the problem is random horizon can be reformulated as a problem with the fixed horizon when up to n max. When horizon maximum value of horizon exactly equals maximum value of support, it's for finite support. If case of support is infinite, we can only produce epsilon optimal policy depends on the tail. And then we need to reformulate the random variable. It's going to be new random variables introduced. And based on these new random variables, which are reformulated based on the old ones, and the horizon distribution, we can reduce problem with random horizon to a fixed horizon. So in this exactly this result that I mentioned. So, and the problem is random horizon, we call assignment problem AP2. So the optimal value of problem AP2 coincides with the optimal problem with a fixed horizon. When we take horizon as a maximum support of its distribution. When in this case, we assume that support is finite. In the case of infinite support, where it's different, we can only give epsilon policy, and it's not presented here. And new job sizes, instead yt, we have yt multiply by this discount coefficient. And then the problem solved exactly in the same manner, and the optimal policy obtained in the optimal value. And this is a result that we obtain by reducing the problem with random and finite horizon to the fixed horizon. Now, I will skip, since there's I don't think there's enough time, I will skip the proof and go to the results, okay? Maybe some questions, if some questions I can answer and then can go. Okay. So now I will demonstrate now. Sorry, I only looking if I will demonstrate now this problem in reduction on the selecting of the k-best values, one of the k-best values with random number of alternatives. So I coming back to the problem, I remind you the problem, and then I will show how everything can be reduced by one method of solution. Now, selecting one of k-best alternatives, as I mentioned, in the literature, it's called Guzey-Zadeh stopping problem. And what we want to do, we want to maximize, based on the information, its relative ranks observed, stop this value, which absolute rank up to absolute rank less or equals to. So Gusein-Zadeh solves this problem by finding optimal policy. In optimal policy, you need to find integers, k integers. And in the beginning, you only you observe pi1 minus 1 observations. You only observe the ranks, relative ranks, but you don't take them. And then between pi1 to pi2 minus 1, you only pick up observation with relative rank 1. If doesn't exist such one, between pi2 and pi3 minus 1, you pick one or two, and so on until end. Until end. If you don't have such, you take last one, and last one can be appropriate or not appropriate, and therefore probability is not 1. For example, if n equals to 30, and you would like to pick up one with the absolute rank less or equals 3, you reject first 10, and then from observation 11 to 17, you're only going to pick up relative rank 1. From 18 to 23, you pick 1 or 2. From 24 to 29, or 1 or 2 or 3 relative ranks. And then if you don't have it until 29 such, you take last one, and what you have, you're going to have. And he also, so Gusein-Zadeh provided dynamic programming algorithm to calculate these values P1, P2, and P3, and also from dynamic programming algorithm, optimal value also obtained. This is classical problem selecting one of k-best. So in his optimal value, yes.
Can I ask? This is to pick one of the k-best.
Exactly, one of the k-best. Exactly.
Is the problem of picking all of the k-best also? Okay,
so the problem, picking of all 3 best, at the end I need to discuss in this case. We cannot solve by this method this problem, because in this case, this can be solved case by case cases, because in this case, we're not able to reduce the if you suppose you want to pick all 3 best, it means 3 stoppings. If you reward 0,1, here it's reward 0,1 probability of expectation of indicator, we cannot reduce this case to the case of independent random variables. Therefore, method not going to work in this case. Not going to work. But if you reward, for example, additive expected values of the ranks, and this total expected values of the absolute ranks, we can solve this problem for additive reward. But for 0,1 reward, we cannot solve. And this problem solved case by case in the literature. To my best knowledge, I only saw solution for the k equals 2 best, because solution it's very tedious in some sense by writing dynamic programming equations and interacting make them to solve. So I only saw solution for 2. I will mention it then, hopefully by time. Now, auxiliary stopping problem can be formulated. I need to introduce auxiliary stopping problem B. Now, what I will show is that generally, this auxiliary stopping problem, our problems A1 and A2 with fixed and radial horizon, with one stopping. If it's only one stopping, it's exactly can be reduced to auxiliary stopping problem. In this auxiliary stopping problem, it's equivalent. A solution can be done by Derman, Liberman, and Ross by assignment problem 1 and 2 depends on fixed on random horizon. Now, auxiliary stopping problem, it's not complicated formulated. It's y1 to yn, it's sequence of independent real random variables with distributions f1 to fn. You would like to find the stopping rule such that expected reward on stopping is maximal. This is auxiliary stopping problem. Now, generally, auxiliary stopping problem, it's Derman, Liberman, and Ross solved this auxiliary stopping problem because you have only one stopping. In this case, you take all p's equals to 0 and only one p equals to 1. And then Derman, Liberman, and Ross can be reduced by very simple stopping rule when you stop first time, when yt more strictly more than some particular value a obtained by algorithm Derman, Lieberman, and Ross, and we call this value b, and this sequence b is a corollary of Derman, Lieberman, and Ross can be calculated in very simple manner. All the sequence b, and where your stopping time tau, it's simple first time when yt it's memoryless threshold rule when you pass particular value of b. And when value, optimal value, it's last value of b, bn plus 1. Optimal value of reward function, it's bn plus 1. So it's this auxiliary problem solved directly by the Derman, Lieberman nodes. Now, what we show that our two problems, A1 and A2, they can be reduced to auxiliary stopping problem, which is solved by Derman, Lieberman, Ross in this whole solution. So how to show it? We can show it by this way. Let's do for first one, problem A1, it's for fixed horizon. In this case, we define I, T, and R as expected reward, given that relative rank, it's in time t, relative rank at time t equals to R. So, and now our new random variables, yt, it's exactly ITN RT. And now our result claims that optimal stopping rule tau, which solves problem B, which random variables yt defined in this manner, given here in 3 and 4, solves problem A1. And this is how we can solve problem A1 with fixed horizon, fixed horizon, using problem B. And then the problem B is solved by the corollary 1 of Derman, Lieberman, and Ross. Now, of course, there is no possibility. I will skip the proof. We generally use direct calculation and the independence of the horizon and the filtration, but we also use result from the book of Chow, Robbins, and Sigmund Great Expectation. But I will need to skip the proof because of time. And we presented implementation algorithm, how we can implement solution in the finding these values B in the simple way. So now, as a numerical value, if we're coming back to maximizing probability of selecting one of the k best, here for different n's in different case, this optimal probability under using the presented algorithm, but because they also the stopping rule very simple form y first time when y larger than value of b, we can calculate also characteristic of a stopping time. For example, we calculated elapsed expected time until stopping, divided by n. It's here. For example, if k equals to, suppose if n equals to 10,000 and k equals 10, say, our probability to select one of three best is 0.97658. And average time until stopping normalized by n is 0.54. So, and we can do it for any possible value k and n in this other characteristic. Now, if we're coming back to the, again, to Gusen-Zadeh problem, this is how our algorithm working. We have sequence B, we have sequence Y, which depends because we want to select in horizon 30, we would like to select one of the three best. We only can stop with relative rank 1 or 2 or 3. Otherwise, absolute rank not going to be 1, 2, or 3. Therefore, have three sequence of Y, which depends on relative rank 1, 2, and 3. And this is exactly working first time when Y larger than B, sequence B. So in beginning, we don't select anyone. And then from time 11, we're going to select observation with relative rank 1. And then from time 18, you're starting to select or 2 or 1. And then from time 24, exactly what Gusen-Zadeh did, or 3 or 2 or 1. And then at any case, you're going to take, if you don't select until time 30, you take last one. Now, second step is to show what possible to be done in the case when the random horizon. So with random horizon, we have a similar type of result. So similar type of result, we need to define new kind of random variables, and then again, reduce to the problem B. So, and now, remember, first random variable in the fixed horizon, it was conditional expectation of QA given relative ranks. But now with random horizon, we need to weight it on the horizon. Depends, we need condition also on horizon. So therefore, our new random variables here, it's exactly its previous case, weighted that at time t, if we arrive to time t, our horizon can be from t to n max. And it's exactly weighted, new weighted random variables. It's kind of conditional expectation weighted by horizon. And now our theorem claims that if maximum support is finite, that optimal stopping rule tau, which solving problem B with fixed horizon n max in random variables yt defined here, provides a solution to the problem A2, the stopping problem with the random horizon. Now, here also, I will need proof it's very similar. Very similar, we only need to consider correct reward function, because at time t, horizon should be at least t. Otherwise, we cannot arrive at time t. And it's exactly appropriate to filtration how we define random variables y. And then, as a demonstration, I can show it exactly Gusen-Zadeh problem, which not generally solved in literature, using random horizon. So if we take horizon uniform on the integers 1, 2 to 30, and again, we want to select one of three best, if exists, of course, on horizon. Again, we have a sequence B, three sequences of y's depends on relative rank 1, or relative rank 2, or relative rank 3. And again, policy here in this case, it became very, very similar. We stop first time, stopping rule always the same type. In the beginning, we don't stop. And then from time, here we stop early because we, previous case, it was fixed support 30, but it's now random support 30. It is maximum, random, now n is random. Now we stop first time from time 4, not 11, it's a previous time, if relative rank equals to 1. From time 10, we stop with 1 or 2. And from time 18, we stop with 1, 2, or 3. And then value, optimal value on the stopping, it's less, it's 0.54, less than this fixed horizon 30, it's 0.54. So it's kind of, this problem, it looks simple, but it's not no solution in literature of this kind of problem, because case by case cases, each problem solved by case, in here everything reduced to the same type. Now, only to make some demonstration, if you're coming back to secretary problem, I said use it, Pressman and Sonin solve it with random horizon, and solution not supposed to be threshold form in their form, because by case. But our solution always threshold form when y, random variables y more than b. And here it's exactly presentation. Here it's classical, I will skip it because of time, but this one, we took random horizon of size 100, we support maximum 100, with the mixture of two inflated binomials. So it has large mass in the beginning and large mass in the end, and more or less zero probability in the middle of values of n. And when what happened, this is red is sequence of B, and blue is sequence of y's. What happened beginning, you don't stop. It's classical secretary's random horizon with this distribution on horizon. And when we stop with relative rank 1 in this range, and when you again not stop, because by intuition it's correct, because there are probability to have this number of observations very close to 0. And then again you started to stop. So, but our rule always the same form, because we need to worry when y first time cross b. Now, I have only 5 minutes, so maybe I will use 2 minutes to last problem, and then we can some questions. Is it okay? Thank you. So if I coming back to the full information problem, Bruce Ott theorem published in the Annals of Probability, Bruce tried to maximize probability to stop with last success, and he found optimal rule, which has a sum of odds. You stop first time when ZT equals to 1, and the sum of odds cross 1 if exist. Otherwise, you stop first time if ZT equals to 1. And he found optimal value. So what we can suggest, we can apply now our algorithm and solve Bruce's problem in this way. We define random variables yt, its probabilities is ZT equals to 1 and rest equals to 0, given information sigma algebra up to time t. And then we need to find maximum y tau based on full information. Now we can apply now Colloquium, and we're going to stop first time when yt larger than value of its particular value of b, and values of b calculated based on Colloquium. And when we obtain, to find this value b from Colloquium, we obtain this recursive equation. What is interesting is that we don't need to use kind of computer, because in this case, we found by iterating this recursion, we found closed form solution that is exactly identical to the Bruce closed form solution by different methods, of course. And this is solution. We solved his problem also. I will skip this slide. Now, to summarize shortly, so we can solve different problems with no information rank dependent reward, and we can solve problems when the observable information is relative ranks of full information, and we can also solve multiple choice problem if you need to do full stopping, but you have additive reward function. What we cannot solve, for example, the problem where reward based on ranks, but we have full information. This type of problems is described in 2007. We cannot solve this type of problem. We cannot also solve a problem what I was asked before, selecting when the reward is 0, 1, and we need to select, for example, two observations to maximize probability of selecting 2 observations with absolute rank 1 and 2. This kind of problem we cannot solve, since we cannot reduce in this type to our method required reduction to the problem when you have independent random variables, not necessarily identical distributed, independent random variables y1, y2, and so on. In this case, we cannot reduce to the case of independent random variables. Therefore, we cannot solve this type of problems. Now, there is many open problems here, and open problems in all these areas. Everything was presented and done here. It's based on the absolute knowledge of distribution. There is not such as many papers when distribution is unknown. And the room for research here, it's all cases when all distribution absolutely unknown, and you're interested in full information, for example, or for example, distribution known in the class, you know distribution up to parameters, and you would like to find the solution. This kind of problems is, there is a few papers, but there's mostly not well investigated, this unknown distribution case. So more or less it's all. I'm sorry, I think I only left 1 or 2 minutes.
Okay, thank you very much. Are there any questions? So there were some questions along the way. Any more questions or comments?
So one really short question.
Yes.
No, go on, Jeremy.
I just wanted to ask Yaakov, not on what you talked about. This you mentioned. I mean, this is just one paper of yours from 2020.
This paper, it's paper, yes, which summarize all these findings. I think we presented 12 different problems as example by solving by unified approach with full or no information. And this one paper from 2020. Exactly.
worked on this beforehand, or you just worked, so this is just recent?
No, I started to work it on this topic when I arrived to the
you said in
2018. Exactly.
2018. Okay.
Now
so,
we're doing some stuff related to the unknown distribution case.
Are you making any progress on this?
Yes, with some stuff, but it's still no paper to present. There's some kind of preliminary stuff, but no paper to present. In fact.
Okay.
So if everything is IID, then why is there a difference between the known and unknown distribution problems? Because after a really short time, you get an estimate of the distribution based on what you already observed.
It's correct, but remember, in order to what happened, it depends on the if you try to solve full information problem, when your observation your observation it's x1, x2, so on. If you try to solve full information, in order to apply Derman-Lieberman-Ross or our modification to Derman-Lieberman-Ross, in order to find this cutoff points in intervals, you need to know distribution. And if you don't know distribution, you cannot solve it. So you can only, of course, you can, if you estimate distribution, you can do it. So it's few ways. Or you estimate distribution by empirical distribution, or you can find maybe some other approach that we referred about. It's kind of minimax type. So if you concentrate on some kind of a class of possible distribution, you can find you can minimize worst case or maximize worst case scenario.
Okay, any other questions? All right, if not, thanks again.
Thanks a lot.
Thanks.